Good afternoon, everyone, and thank you for joining us for this webinar. In this session, we're going to introduce you to NetStream Primo 10G, which is a new product of Netronics working in 70 to 80 gigahertz. It's a point-to-point device, and it's providing 10 gigabit per second of throughput, which is a breakthrough capacity. And we're going to get introduced today to the technology and the features of this product. So the agenda for the session today is introduction to millimeter wave. We will go through the benefits or limitations of this technology. Then we will overview the product in terms of general aspects of how the product is formed and how can you use it. Antenna alignment is another topic we are going to cover because this is a very important aspect of this technology. If you align the antenna properly, you can rest assured that the rest of the installation works fine. We will see some performance benchmarks, and we will see in what distances you will get what capacity, which is very important to understand how useful this product can be for your network. Then there will be some use cases, and there will be a summary at the end. So now we go through the introduction to millimeter wave. Millimeter wave, the name is coming from the fact that when the frequency increased to a certain level, the wavelength becomes a couple of millimeters, and that's why we call it millimeter wave. But why this millimeter wave is becoming so interesting? The reason is the need for more capacity, which is increasing all the time because new applications are coming, millions and millions of new people are joining the networks, and also the pattern of use is more towards video and more capacity consuming applications. So the need for capacity is leading us to the need for larger channel bandwidth in the links, because the capacity comes from the channel bandwidth. The more the channel bandwidth, the capacity is more. But the channel bandwidth is limited in lower frequencies because it's an asset that is under a lot of demand, and that demand is making it less available. So the only way to go over this capacity limitation is utilization of the unused frequencies. So if you look at the spectrum of frequencies, on the horizontal, you have the frequencies. On the vertical axis, you will have attenuation of the air. So you see on each frequency, there's attenuation of the air. You see different colors, but we will look at the green one, which is the total. The blue one is predicted by oxygen, and the red one is coming from the water vapor. And the total is the one that we have to deal with, because both of those parameters are in effect. So we deal with the green one. If you look at the frequencies, you see there are some frequencies in which there is a dip in the green curve, which means that in these frequencies the attenuation is less than the other frequencies around it. And there are peaks. So you can see around 24 gigahertz there is a peak. So no wonder why the 24 gigahertz is a license-free in many countries, because this is the frequency that the operator is not interested in, so they make it license-free. So there's another license-free frequency around 60 gigahertz, as you can see here. So if we want to use new frequencies, the sub-6 is very well heavily used by sub-6 equipment, which are cheap and in large quantities available. Then up to 42 gigahertz is already used by microwave. So we have to find a frequency over 42, which is not used. And in that frequency, we should see the least attenuation. So if 5 gigahertz is here, then another interesting frequency is around 26 to 30 to 42, which is the microwave. And the other deep in the curve is around 70 to 80 gigahertz. So this is where the millimeter wave is working, and this is called the E-band. So if you look at the spectrum, on the left you will have lower frequencies like 2 gigahertz, and on the right you will have 81 to 86 gigahertz, which is the band called E-band, which we are going to introduce in this session, and we call it millimeter wave. So in 2 gigahertz, and the proportion in this slide is not correct because the correct proportion would be not readable. So it is a bit exaggerated in 2 gigahertz and less width in the higher frequencies. So 5 gigahertz, then you have the whole microwave, which is around 6 to 42 gigahertz. Then you have the millimeter wave. And in millimeter wave, if you separate transmit frequency and the receive frequency, which is around 70 gigahertz, you will have a diagram like this, which, as I said, is not proportionally correct. The lower frequency should be much, much more narrow. But if you look at the channel size in each of these frequencies, if in 2 gigahertz, you can have like 2.4 gigahertz, the old Wi-Fi, you will have 15 to 20 megahertz of channel. In 5 gigahertz, you will have 40, 80 maximum, or in new radios, 2 times 80. Even that, in 5 gigahertz, you will have a proportion like you see in the screen. In microwave, the channel size is sometimes even less because this is the paid frequency. So the operators are trying to minimize the use of spectrum. So maximum 56, 80, and rarely it is seen more than that. In millimeter wave, the channel size can be around 2 gigahertz. And the 2 gigahertz is not the frequency, it's the channel size. So you occupy 2 gigahertz between 71 to 76 for RX, and between 81 to 86, you occupy another 2 gigahertz for TX. So for transmission and receive. So this is leading to a very big channel size, not comparable with whatever the wireless radios you have been dealing with. And this will lead to very large link capacity. That is why we are able to reach 10 gigabit per second over the air, which is a huge capacity. So another benefit of millimeter wave is the antenna beam width. This is a benefit, and this is also a challenge. We will see it in the next few slides. In 5 gigahertz, this is a 5 gigahertz radio of Netronics, NetStream 5X750, for example. The beam width is around 2 to 4 degrees. However, in the millimeter wave, the 1 foot antenna will have a beam width, which is again proportionally not correct in this slide, should be much, much more narrow. The red beam should be much, much more narrow than the blue beam, and it's 0.1 to 0.2 degrees. So it's a very pencil sharp, very narrow needle shape beam, which is between the two antennas. So how this narrow beam is going to help us? This narrow beam is eventually leading us to no interference, to an environment in which there is almost no interference. First, there is no interference because the frequency is very high, and there is very limited number of radios today in this frequency. But that's not all. Even if the number of radios increase, still there won't be any interference. You will see in the next slide. For people who live in UAE, this is very familiar. This is showing you Deira in Dubai. So we will have an example of a site which is trying to transmit 5 gigahertz using a normal 5 gigahertz antenna. So this antenna is illuminating an area in front of it. But because in that area, because of the width of the antenna, this is a big triangle and it goes very far. So there might be other sources of interference working in the same frequency because this is a free frequency. And then this we are talking about 5 gigahertz, it's blue. So there are many sources of interference in front of the radio because of the beam width, and you will end up with a spectrum which is almost completely full. So it will be very difficult to find a place in this spectrum in which you can have legitimate and stable wireless link. Whereas when you use millimeter wave, the beam is very narrow. So maybe in the future, once millimeter wave becomes very common, there will be the same number of radios, but because the beam is very narrow, they are out of my beam, so I don't see them. So the radio will not see them, and you will have a much, much cleaner spectrum. So it's not just because there are not many radios in millimeter wave today. Even in the future, if there are thousands of millimeter wave radios, as much as the number of 5 gigahertz radios of today, still interference will be much, much less than today because of the needle sharp beam. So this is an example of number of links in a city. This is Bay Area, San Francisco Bay Area, which is a very busy technically. This is where Apple and most of the silicon companies are. So demand for capacity here is huge. So since 2012, there have been increase in the number of links here. 2016 and 2018 and 19, you can guess what is going on. So there's thousands of links, but there's a still spectrum to be available because the beams are very sharp and interference is not a problem. So another advantage of millimeter wave is that it is future proof. Once you install it, even in the future, there won't be much of interference. Whereas in the other frequencies, even today in some countries in microwave frequencies, we have interference in 8 gigahertz in some of the countries because we have installed a lot of 8 gigahertz microwave links. So we are ending up with having interference in microwave as well. But in millimeter wave, this is not happening. There are limitations, however, about how millimeter wave is going to give us advantages. Distances are limited. So in millimeter wave, you do not consider millimeter wave as your solution if the distances are bigger than 15, 20 kilometers, depending on the city, depending on the rain, depending on the humidity. And we will go through this, what parameters are affecting it. But if something is around more than 15 to 20 kilometers, millimeter wave is not your solution. So this is very much limited to lower distances. In the past, this distance limitation was very much severe, so you could have 1 or 2 kilometers and no more. But with our radio, because of the highest link budget in the industry, you can go distances that were before not available with millimeter wave. And on the other side, when you have a very huge capacity of 10 gigabit per second, you don't go very far because you will go beyond where the civilization is happening. If you're within a city and it's a populated city, there's a very high chance that within 15 kilometers the city will finish. So you don't do backhauling between the cities with this, and within the cities you will be less than the distances. I mean, most of the links will be less than the distances that you will need for this kind of capacity. The other limitation is weather sensitivity. Because in millimeter wave, you have the wavelength couple of millimeters. So if there is rain, the droplets of rain will have size of couple of millimeters, which are equal to the size of the wavelength. So this will enforce a very large attenuation in your link, and the attenuation will make the link not available when there's heavy rain. But this depends on the number of minutes of rain over the year and the environment. So the weather conditions of a city would affect the performance of a millimeter wave. But on the other side, in Middle East, there are many highly populated, very highly densely connected, wirelessly connected cities like Riyadh, like Dubai, like Kuwait, like Manama in Bahrain, or like Doha, which are not very wet cities. So we have many cities in this region in which rain is not much of a problem, but demand for capacity is more. So there's a very good opportunity for this product in the region of Middle East. So this brings us to the overview of NetStream Primo 10G. You have two main products here, which is the product with 1-foot antenna and the product with 2-foot antennas. Basically, the antenna is not attached. So basically, you can order the radio and then you can order the antenna of your choice, and it works with the radio. Before it was attached, but now it's not. So the radio comes separately with a flange, which can get connected to a 1-foot antenna, or it can get connected to the 2-foot antennas. For the 1-foot antenna, mounting kit is attached to the radio, and the antenna is attached to the radio as well. In the 2-foot antenna, because of the size and the weight of the antenna, the mounting kit is on the antenna, and the radio is attached behind the antenna. So in the 2-foot, antenna is connected to the pole. In 1-foot, the radio is connected to the pole. If you look at the ports of the product, you will have a DC port, 48 volt, normally a positive ground 48 volt, which you can power it with DC. You can also power the unit with the PoE, and it comes with a high power PoE injector, AC high power PoE injector. Then there is a 10 gigabit combo ports, which you will have one SFE port and one gigabit electric port. And also you have the RSSI meter, which you can put a multimeter, and you can see the RSSI level, and you will use it during the alignment. There's a USB socket, which is reserved for future. So you have power and management port. You can power it with DC or PoE, 50 watt. And also you can connect it with the fiber or copper. So both options are available. The capacity licensing is 2, 5, and 10. That is because most probably you don't pay for a 10 gigabit per second and use it for 2 gigabit per second. But if the capacity in the beginning is less, you don't have to pay for the 10 gigabit, although the link is capable of doing 10 gigabit. Then you can upgrade it to 5 or upgrade it to 10 gigabit per second. So pay as you grow option is available. The channel sizes available are 250, 500, 1250, and 2000. 2000 megahertz is the one that gives you the 10 GB. There are priority levels. Basically, this unit is a very intelligent switch, which can do many functions between the ports, and the QoS is one of those functions. AES-128 encryption is available in some of the models, depending on which model you use. And there is a dynamic booster. When the rain is coming, the device can sense that the RSS is less, so it will ask the other radio to increase the power if there is room for increase to keep the modulation and to give the maximum capacity. In terms of mechanics, you're looking at a radio of 21 centimeter by 27.8 centimeters, almost 11 inch by 8.2 inch, very close to an A4 size paper, very close. If it is attached to a 1 foot antenna, it would look like this. There is a half foot antenna. We don't see much of opportunity for this antenna in this region because this is for very short distances, less than a kilometer. And this is where the size of the antenna matters in some countries in terms of aesthetics of a street or the rooftop. We don't see this happening in this region. The 1 foot antenna, 30 centimeter, and the 2 foot antenna, which is 60 centimeter. You saw them in the previous slide. Antenna alignment is a key element in millimeter wave. So if you're in millimeter wave, you have to be very careful about antenna alignment. The reason being the beam is very, very narrow. So you can go misaligned very, very easily. Here in this slide, you will see the main loop, and the first side loop and second side loop. This width of this beam is very much exaggerated in order to provide a graphically viable, graphically pleasant way of talking about how the main loop and the
Hello, I think we lost the voice for a second. So it is very much exaggerated here in order to provide you a better vision of how the beam is formed compared to the second or third beam. Basically, the red one is much, much more narrow than what you see here. But the proportion is somehow correct. The idea is that there is a main loop, which is the red one, and we are aiming to have these red beams of the two antennas coincide with each other, and we have a link on the main loop. But there's a good chance that we are on the side loop, and we believe we are on the main loop, and that's where we get less RSS, shorter distances, and lower capacities. And this slide is meant to address this confusion, and you will see it in the next slide. So if you stand in front of the antenna, you will see a main beam, you will see a circle of this first side loop and a circle of the second side loop. So imagine we are in front of the antenna and we are scanning from the left to right. So if we scan from the left to right, along this line, if you see my mouse, you will see a graph like this. So you go to the left, you see nothing. You go to the right, you see some signal. Then you go to the right further, and you see no signal because you are hitting the second side loop from the side. If you're a bit higher, if you're a bit closer to the red, you will see two small indications of signal. If you're a bit higher, you will see the first side loop as well. So you see two small indications of signal and the bigger indication in the middle. This is the one that is very much misleading. You might imagine this is the main signal, but this main signal is too weak and you will get less capacity. If you're a bit further, closer to the main loop, you will see two small and two bigger signals. Because you're hitting the yellow, then you hit the orange, then you hit another orange, then you hit another yellow when you scan from left to right. And that's where you tighten the screw that is keeping them fine tuning, and it's moving from one side to the other side. Only when you are hitting the main loop, you will see a very strong middle and two smaller sides and maybe a third smaller signal. And this is the only right alignment, and the other ones are all less than the perfect, and you will get less capacity, less distance, and not a very well functioning link. This is what is the main trick of alignment of a millimeter wave link. If this is understood and if this is practiced, the other parts are really easy. So in order to help you get an antenna alignment with 0.1 to 0.2 degrees in distances of 15 kilometer, 10 kilometer, in those distances, we have to provide you with some help. The help is coming from a telescope which is attached behind the radio with a very strong arm, which doesn't have much of flexibility to bend, so it will keep it very, very strongly attached to the radio. Then on that arm, a telescope which is very much like the telescope you use in a sniper, which is trying to find a very small aim in a very large distance. So this telescope is installed on this arm, and you can move the whole thing, the whole infrastructure, you move it along. So the telescope is showing you where the signal is hitting. And once you see the other side of the antenna, other side of the link, so that the antenna on the side of the link comes within the vision of the telescope, your alignment is almost correct. Then you have to practice the left to right, then right to left, then up and down, so to make it fine-tuned. But the general tuning can be done with a telescope. The main tuning is happening with a multimeter, which is attached to the ports that I just showed you before. And for every 0.1 volt, you will have 10 dB. So every 0.01 volt is 1 dB. So if you have 0.44, this means you have minus 44 dB of power. So minus 45 and less than that is a proper link. So we have tried to achieve anything above minus 45. Can be minus 40, minus 35. All of these are good. Anything less than minus 45, like minus 47, minus 48, these are minus, and the bigger number is less. So minus 47, we try to further align it in order to get the better capacity. Remember, we said the distance and the weather are the two weak points of millimeter wave. We could address one of them, which is the distance, with the technology that we will introduce in this slide. You probably know about the availability ratios like 99%, 99.9%, then 49, then 59, which is 99.99. This is the percentage of uptime of a link over a year. In an example, 99% is a link that is allowed to go offline almost 3 days a year, because 1% of 365 is 3.6 day it is allowed to go offline. So this is not a very much dependable link. If it is 99.9, it's less. And when it goes to 99.99, the link is really stable, and it is allowed to have 5 minutes of downtime all over the year. And that 5 minutes can happen between 2 to 3 a.m. in a cloudy day. So the 99.99% is a very highly available link. So between 2 nines and 5 nines, there are different levels. So in order to achieve a longer range, whenever the link is disconnected, if we have a way of covering the time that the link of millimeter wave is disconnected with another link, which takes over in that 1% of the time, then we will have a link with higher availability actually. So in terms of mathematics, the number of minutes that the link is not connected is counted. So if we can decrease the number of minutes that the link is not connected, then we have increased the availability of the link. This is achieved by having a link on a different frequency in parallel with the millimeter wave link. So you have a main link and you have a link in parallel. So anybody can do this. You can put a switch and you can have a second link, and with redundancy and a spanning tree and other technologies, you can achieve this. But the thing is, we are achieving it without all of this luxuries and without the cost of secondary networking devices. It's hitless. It happens in less than 50 milliseconds. And even the radio of millimeter wave and the radio of 5 gigahertz can be connected to a single antenna. So there will be single antenna. We have a part number for a single antenna, which can work with 5 gigahertz as well as millimeter wave. So in this diagram, you can see that there is a cable, standby cable. So traffic is coming from the other ports, and there is a standby cable that goes to a 5 gigahertz, or this can be a microwave as well. So it can be a microwave that does 1 GB, and whenever your 10 GB is disconnected due to heavy rain, a 6 or 8 gigahertz 1 GB link or 2 GB link is taking over. So basically your link is always available, so there is no time that it's not unavailable, so you can achieve 99.99. This will make it possible for you to go longer distances. Without this second link, you have to stick with an available link and we have to come closer. So this is extending the range. That is why the technology is named range extend. So the recovery comes from the switch to backup when the capacity degrades, and it is hitless and monitoring availability and uplink so that the 10G will come back whenever it's possible. So this is a picture of the antenna, which has, you can see, a ubiquity 5 gigahertz link, which is taking over within those few minutes to few hours that over the year, your 10 GB link is not working due to heavy rain, due to other weather conditions that might make your millimeter wave unavailable. Without this, you would be limited to, for example, 2-3 kilometers. With this, you can go 10-15 kilometers. You will see it in the next slides. So here, the question is, millimeter wave has been there, E-band, there have been products in E-band. What is Netronics offering on top of others, and why we are so excited? We are excited because we have the highest link budget in the industry. Means we go further than anybody else, or in the same distance, we are more stable than anybody else. So the link budget of 164 dB with 1 foot and 178 dB with 2 feet, these are major numbers that would predict how available or how far your link can be. So this is real life performance benchmark from a link in Dubai. Why we talk about Dubai, or why we specify the city? In millimeter wave, we have to understand that the link budget calculation is depending on the city, depending on the location. So if your friend in another city, in a different country, or in the same country but different city, has achieved 5 kilometers with our product, it neither will tell you that you will get more or 5 or less. You have to calculate it for your own city, and we are ready to do it for you. You just give us GPS coordinates on an email that is mentioned at the end of this presentation, and we will calculate it and we'll send it to you, and it's free. You can do that 5 times a day. It's no problem. So this is for Dubai. Considering the weather conditions of Dubai, with a 1 foot antenna, you will achieve a table like this. So let's introduce this table because we will have a number of tables like this. So on the left, you have length of the link. So you have every 500, there is a line. So we will see what happens when the link goes further. Then you have RSS, which we don't care much in this presentation. Then you have 99, then 99.9, then 99.95, we call it 3.5/9, then 4/9, then 4.5/9, then 5/9. So the first row is telling me that I will have 99.995, 4.5/9, I can have in 1 kilometer with a 1 foot antenna. Remember, this is a 1 foot antenna. So the size of antenna can change this. And it's in Dubai. You change the city, it can change it. But this is telling me up to 3 kilometers, I will have 10 GB full capacity up to 3 kilometers in Dubai with 1 foot antenna. And why I care about 99.9? Because this availability is enough if I use a second link in order to increase the availability. So we care about this first column. So 10G is happening at 3 kilometers. If it is more than 3 kilometers, capacity will come down. Still, substantial capacities. Look at 6.5 kilometers. It's 4.25. There is no microwave that does this with single link, single radio. So you can see at 10 kilometers, you will reach 700. I agree with you. I don't buy a 10 GB radio and use it for 700 megabit per second in 10 kilometers. So this is not where we want to be. So now we talk about 2 feet antenna. Now you see how does it increase the distance. You can see up to 6 kilometers you can have 10 GB, almost double, because you double the antenna. So 6 kilometers, almost 6.2 kilometers, you will see that you still have the 10 GB. Again, you can see around 10 kilometers, still you have 4.25 gigabit per second. And this is coming from our link budget calculator, by the way. This is coming almost from the field, and this is very much conservative capacity. Means you will get this or you will get more. You will not get less than this. So another example, now you see if you change the city, what will change. You saw what will change if you change the antenna. Now you see what will change if you change the city. You change the city to Saudi Arabia, Riyadh. What is different in Saudi Arabia is humidity. Dubai being a port beside the sea, it's a humid environment. In Riyadh, you don't have that much of humidity, and it's a 2 feet antenna. It's interesting to see that 15 kilometers, you can do 10 gigabit per second. This is not the number you can see in any other E-band radio. 15 kilometer is not what E-band radio is known to cover, but we cover it, and we cover it with full capacity. This is because Riyadh is not a humid city. So if you go further between 15 to 17, you can see if we go with less steps of distance, it's happening between 15.3 kilometer and 15.4 kilometer. This is where the switch from 10 GB to 8 GB is happening. So if you're concerned about the full capacity, 15.3 is the number in Saudi Arabia in Riyadh with 2 feet antenna. So this gives you an idea about what Netronics is bringing to the E-band. We're bringing more stable and more going further distance with higher capacity radios. So the use cases, where do we use it? Where do we use it? This can be, first of all, there's not only 10 GB. There's a version of this radio which is 1 GB, which is much, much cheaper, and much cheaper than what 1 GB in microwave would be. So if you have a link which is not very far, like 70, 60 kilometers, if you have a link within less than 10 kilometers, and you want to have a 1 GB capacity, if you look at microwave and if you look at millimeter wave will be cheaper. So you pay less and you will still get 1 GB. Now, coming back to the 10 GB, which is the subject of this presentation, one of the applications is to connect a served building with a core network. So do you have a building which is not connected to the fiber, and you want to connect it to another building which is connected to fiber, so you can enjoy high capacity of fiber. So this is, you're actually extending the fiber. So this is another for people who are in Dubai. This is familiar. This is Business Bay in Dubai. So imagine here, there is a hotel complex named M Hotel, and they are behind a channel. So this channel is stopping the fiber, for example. Let's assume it's in a scenario that the channel is stopping the fiber to go there, or the operator doesn't see much of interest to cross this channel just because to serve the other side of the channel. Any scenario like this, which water, a highway, a park, or another obstacle is stopping the fiber to go beyond, and you need capacity beyond that is obstacle, then you can use the millimeter wave to connect the buildings and you can extend the fiber. Another application is extension. I mean, the networking between the different buildings of the same enterprise, which are connected normally with a lease line. So replacing the fiber or backing up the fiber is another application of a 10G link. In backup, we see many scenarios in which we are backing up an IP/MPLS lease line, which is paid thousands of dirhams or thousands of dollars or thousands of reals in a year, and they are doing a backup for that IP/MPLS link. And after a while, they understand that the backup is more reliable and cheaper than the main one. So we had a scenario with a bank in Dubai, and the bank was using a high-capacity IP/MPLS, and they were paying a fortune in order to keep it. Once we installed the wireless link between the buildings, they saw that the wireless link is first giving them higher capacity, and it's actually, once they bought it, it's free. So they downgraded the IP/MPLS to 1/10 of the price, 1/10 of the capacity, and now the IP/MPLS is the backup for wireless, not wireless backup for MPLS. So they were saving a lot on the lease line cost because the ROI is very fast, return on investment. So the number of months of the IP/MPLS rent that you save and you pay upfront and you buy a radio. So after that number of months, your connection is free because you already paid for it. Another application is to form a ring. You know that ring has a natural resilience to failure. So any part of the ring fails, the other direction can take over. So another application is to provide a mobile carrier or WISP ring in order to provide resiliency. The radio comes with 10G copper, which is making life much easier when you want to upgrade an existing link, because the cable and everything is copper, so you don't have a fiber infrastructure in the site. So once the radio is copper, 10G copper equipped, so you can use the same cable if it is Cat 6A up to 100 meters and if it is Cat 5 up to 55 meters and use it for 10G. The management comes with a very intuitive and very interesting GUI, which provides you with all the information. Also, you can use CLI and you can use SNMP, and syslog is also supported. You can do in-band management, means through the link you manage the device, and you can have a VLAN for management, so you can manage the whole network from one NOC through the link itself. Or you might choose to have out-of-band management for There is an installation wizard which is very intuitive, very simple to install, and it takes you step by step through the process of installing the link. You can buy the capacity license in steps. So you can start with, you can keep the stock of radio with no license. Then you can add a 10 GB license when you sold the device, which is very useful in terms of saving the money. You don't want to pay for a license and put it on a shelf. Once it is on the shelf, it's less priced. And once it is installed, you pay for the license. Or you can use you can install a 10 GB link because you predict 10 GB will be needed. But today you don't need 10 GB, today you need 2 GB. So you pay for a license of 2 GB. So the cost is less for the couple of months, couple of years, until you grow to 10 GB, and the 10 GB, you pay for it when you need it. NetStream Primo 10G, the summary is we have the best range in the market, 64 dB system gain, and we have different media supported and the different capacities supported by licenses. It's a trusted solution. It's different portfolio. We will introduce very soon the point to multipoint in millimeter wave, which is another very interesting product with very attractive price tags. It's the longest. We are providing the longest range in millimeter wave in E-band, and the cost per megabyte is the lowest in the industry, because the 10 GB comes in a price that if it was microwave, it would be 3 to 4 times more expensive. And operation, installation, and maintenance is very simple. So this was the content of the presentation. If there is a question, there is a Q&A feature in your application. If you have a question, we will be ready to answer that. If not, thank you very much for your time.